大家好，我是心灵。今天呢，我用 CourseWare 给大家做一个 demo，用的呢，topic 是 physics，因为我们家孩子正好正在学 physics 哈，咱们就用 physics 作为一个 demo 吧。在 CourseWare 里面呢，它每一个科目别的科目我不知道哈，physics 这个科目呢，它有 semester A 和 semester B，就是第一学期和第二学期，一个学年分2个学期 A 和 B。然后在那 A 里面呢有6个 unit，然后 B 也是6个 unit。那每个 unit 讲的是什么东西呢？它会有个 course syllabus，你点开的话就可以看到它的东西，然后它有 course requirement，像数学和科学的基础的要求。数学的基础要求就是 algebra one，algebra one 就是代数，然后还有就是几何 geometry。好了，其他也就没有什么别的要求了。对，然后至少会读一些英文吧，可能就是这个要求，然后没有了。OK，它有一个大概的，就是说 suggested number of days you need。So 他们认为呢，你把这个科目自学的话，差不多，如果没错，它90天，他认为90天可以自学完成。所以，照着他的就是 suggested date 去做，还是不错的哈。那每一个章节呢，就是每个 unit 底下呢，又分好几个 section。那每个 section 呢，它都有一个叫做它有个章节的 pre-test，这个 pre-test 是针对整个 unit 哈。然后呢，完了之后它就有一个就是说每个 section 呢有一个 tutorial 就是 lesson 的意思，就是在教你哈。然后呢，就有个测试，这个测试我们称之为 mastery test，就是看你是不是真的懂了。好，那我们进到课程这个是 syllabus， 我把它关掉了哈。那么课程刚才我已经打开过，你如果一打开这个账号呢，其实是没有声音的，但是你可以设置声音。我们先做一个设置没有声音的版本做 demo 哈，然后你看一下，它这里有个箭头，表示你可以 play， 这个是往后重新开始，这个可以把声音关掉，你不点它就没有声音啊。像有的人读得快，你可以就过去了，然后下一页。然后下一页的话呢，好，这个大家读起来也很快哈，你可以不读，也可以让他读。你看，我们让他读一下。
In this lesson, you will define physics, consider how it relates to other sciences, and examine how scientists have contributed to our understanding of the physical world.
我现在用的版本，现在用的模式是手动模式。你看到我其实一直在点这个箭头，我可以向后，也可以向前。这个呢是适合有些小朋友，就是他喜欢自己控制，像有的东西他们读书读得很快，他这个一页就啪跳过去了，那他就直接走下一页。然后这个呢，有的小朋友读书读得很快哈，他就自己去肉眼去看，很快。那我呢，英文不是那么好，对不
Introduction.
对？那我就听一听。
William is playing his new online game Peacemaker with players from England, India, Mexico, and Canada. Together, they plan and propose ideas to promote peace in the Israel-Palestine conflict. The group plays the game online using an internet connection that is routed through a communications satellite orbiting Earth. The players may take for granted this modern technology, which enables people located thousands of miles away from each other to communicate in real time. They probably don't know that this technology is rooted in the discovery of rules that govern the movement of heavenly and earthly bodies. Many scientists contributed to our understanding of these rules, but the pioneer among them was an Italian scientist who lived more than 400 years ago, Galileo Galilei. When Galileo first turned his handmade telescope toward the night sky, the sheer beauty of the sight amazed him. He wasn't only interested in the beauty of nature, however. He wanted to know how nature worked. Galileo made observations using his telescope, which could magnify objects to more than 32 times their actual size. His observations and conclusions led to discoveries that intrigued and fascinated some people. Others were enraged because his findings contradicted the beliefs of the Catholic Church at that time.
你们仔细听就会发现，其实这个配音配得非常好哈，像它重音的地方都会读得比较特殊一点，所以呢，其实我觉得听一听也不会没有什么坏处，但有的人读书真的很快，那就 skip 掉哈。那我们去看下一页。你看我也可以不让他说话，也可以让他说话，对吧？我点这个模式，但是呢，其实还有一个模式，你说，哎呀，我这个人嫌点太麻烦了，那我就点一下这
Based
个
on
模式。
his discoveries and his studies, Galileo concluded that Earth was not a large center of a small universe, but rather a small body in a much larger universe. His conclusion overturned Aristotle's theory, which stated that Earth is a stationary body and all other heavenly bodies revolve around it. Galileo became the first scientist to discover that the Sun is the center of our solar system and that all planets, including Earth, move around it. Let's take a closer look at the life of Galileo, who is now regarded as the father of modern science. Galileo was born on February 15, 1564, in Pisa, Italy. Although he first aspired to be a doctor, he became a physicist, astronomer, and mathematician. Most of his contributions came from a combination of experimentation and calculations.
虽然我已经让它去自动读，但是它那个翻页好像还要靠我自己来我翻页。
Galileo was well known for the method of inquiry he used to understand events. His most significant contributions to physics were the discoveries of the fundamental principles of motion. For example, he discovered that when two objects of different masses are dropped from the same height, they hit the ground at the same time. He was also the first to define speed as the ratio of distance traveled to time taken. His observations of the stars of the Milky Way led to the hypothesis that the Sun is embedded within a disk of stars. Many of Galileo's observations challenged Aristotle's ideas, which had been accepted as true for centuries. In fact, his observation that the Sun and not Earth was the center of the universe was strongly opposed by the Catholic Church. For this reason, in 1633, he was sentenced to house arrest for the remainder of his life. Galileo is considered the first true scientist and the first physicist, but many more followed in his footsteps. Let's begin our study of physics by looking at a few of the other pioneers who helped describe how the universe works. Timeline. Pioneers of physics. Click each event on the timeline to learn more about physicists who have made significant contributions to the field. Use the controls on the left to expand and contract the timeline or to return to the beginning. Timeline. Pioneers of physics. Click each event on the timeline to learn more about physicists who have made significant contributions to the field.
Sun. Nicolaus Copernicus was a Polish mathematician and astronomer. He was the first scientist to dispute the idea that Earth was the center of the universe. Instead, he proposed that the Sun remained stationary in the center and Earth revolved around it. This theory was known as the heliocentric model. Copernicus proposed a direct relationship between the distance of planets from the Sun and the size of their orbits. This relation meant that a planet closer to the Sun would have a smaller orbit than one farther from it. At that time, Copernicus's ideas were hugely controversial. Still, they were influential, and the world started looking at the movement of celestial bodies in a different way. The heliocentric model was later supported by Galileo. Because of his ideas, Copernicus is considered the initiator of the scientific revolution. 1564. Galileo Galilei, 1564–1642. Galileo Galilei was an Italian physicist, astronomer, and mathematician. He supported the heliocentric view, stating that Earth and other planets revolve around the stationary Sun located at the center of the solar system. His support of this model drew opposition from some philosophers and clerics. Ironically, his book Dialogue Concerning the Two Chief World Systems, 1632, in which he justified his stand, became one of his most famous works. He also began work on a book on motion, De Motu, but it was never published. Galileo's fascination with telescopes led him to discover sunspots, to make observations about the surface of Earth's moon, and to discover Jupiter's 4 largest moons. Unfortunately, the telescopic observations of the sun damaged his eyes, and he became blind at the age of 72. 1643. Isaac Newton, 1643-1727. Isaac Newton was an English physicist and mathematician. He is considered to be one of the most influential people in human history because of his work to define classical mechanics. Newton's 3 laws of motion concern inertia, acceleration, and action and reaction. These laws describe the relationship between the forces acting on a body and the body's motion due to these forces. Newton also investigated the phenomenon of light. He invented the first reflecting telescope. This instrument was smaller than the conventional refracting telescope but had impressive magnifying powers. Using prisms, he discovered that white light is a mixture of a rainbow spectrum of light rays. He inferred that different colors of light bend at slightly different angles when entering or leaving a transparent medium such as water or a glass prism. Newton's conclusions about universal gravitation and the 3 laws of motion were so fundamental to the field of physics that we still describe most of the physical phenomena we experience as Newtonian mechanics. 1706. Benjamin Franklin, 1706-1790. Benjamin Franklin was always curious about how things worked. This curiosity, and his interest in making some money, led him to invent a host of useful devices. For example, he was curious about lightning, so he tried some fairly dangerous experiments with kites. These experiments proved that lightning is a form of electricity, which could be carried by a conductor into the ground. Franklin took this knowledge and invented the lightning rod, still used today to keep buildings from catching fire when lightning strikes. Franklin had poor vision and needed glasses to see both far and near. To avoid the inconvenience of juggling between 2 sets of glasses, he cut the lenses of both glasses in half and then put half of each lens in a single frame. Voila! Bifocal lenses. Franklin is also believed to have invented the first flexible urinary catheter, apparently to help his brother who was suffering from a kidney ailment. His many voyages across the Atlantic led him to learn about ships, and he improvised a model of a ship with watertight compartments. If one compartment sprang a leak, the water would not spread to other areas, and the ship wouldn't sink. He also invented a highly efficient household heating system known as the Franklin stove. Navigate to previous slide. Timeline. Pioneers of physics. Navigate to next slide. 1000.
OK， 好，在这个系统呢，在他自己读的时候，他会去重复，所以我们可以停下来了哈。然后我们看下一页。
What is physics? Physics is one of the 3 main fields of science, the other 2 being biology and chemistry. If asked what biology or chemistry deals with, most of us can come up with a one-word answer, life and chemicals, respectively. But to answer what physics deals with, you may come up with a long list that includes motion, magnets, machines, light, sound, and electrical circuits. What common thread runs through this list? Everything on it makes up part of our physical world. Physics is the scientific study of matter and energy and their interactions. It's a basic science that deals with motion, electricity, energy, heat, sound, light, atoms, nuclear physics, and astronomy, among other topics. These areas of study can be broadly classified under two fields: classical physics and modern physics. Classical physics includes the study of motion, electricity, energy, heat, sound, light, and magnetism. Modern physics deals with topics such as nuclear physics, atomic physics, astrophysics, and relativity. Let's take a closer look at some fields within the discipline of physics. Mechanics. Mechanics is the study of energy and motion for bodies affected by a system of forces. There are four basic forces known in the universe. Two of them, quantum forces and nuclear forces, apply only to nuclear interactions. The other two forces are gravitational and electrical forces. These two forces are the root causes of all the day-to-day physical events we experience. Scientists such as Galileo and Newton were the pioneers of this field, known as classical mechanics. Classical mechanics was the first branch of physics to be discovered. It laid the foundation for all the others. Properties of gases, liquids, and heat. The laws of mechanics apply all the way down to the atomic level. But if you want to know how 10 to the power of 23 molecules will behave in a small bottle, you don't need to analyze the motion of each molecule. Large numbers of molecules behave as a group in predictable ways, and knowing how they behave is useful. Scientists such as Robert Boyle, Jacques Charles, Joseph Louis Gay-Lussac, John Dalton, and Amedeo Avogadro studied the behavior of gases and the relationships among pressure, volume, and temperature of a sample of gas. They developed various laws that could be applied to all gases. In the same way, scientists have studied the properties of liquids with respect to their volume, pressure, buoyancy, and flow. In physics, heat is studied as thermal energy. The study of how heat is related to pressure, density, and temperature is known as thermodynamics. Waves, light, and sound. The laws of mechanics apply to waves on a spring, in water, or in air. All waves have some similar behaviors and properties. Knowing those properties can be very useful. Wave properties, amplitude, frequency, and wavelength, for example, have various applications in physics. We study these properties when we study light, sound, or periodic motion. Acoustics is the branch of physics devoted to sound and sound waves. Acoustics also includes ultrasound, infrasound, and vibrations. Acoustics applies to almost all aspects of our daily life, most obviously in the music and audio industries. Acoustics is also widely used in medical imaging. Optics is the branch of physics concerned with the behavior and properties of light. The laws of optics also have wide application, especially in the development of different types of lenses and mirrors and of the fiber optic networks that now connect the whole world. Because light is an electromagnetic wave, the laws of optics can also be applied to other forms of electromagnetic radiation, including X-rays, microwaves, and radio waves. Electricity and magnetism. Physics also includes the study of electricity, which is one of the four basic forces of nature. Electricity plays a major role in technology and everyday life. Electrical charges follow the laws of mechanics, but like molecules in a gas, their behavior in large numbers is often more interesting and useful than their individual behavior. Electricity appears in nature in different forms, the most prominent being lightning. It's an extremely flexible form of energy that can be put to many uses. Think of all the different electrical appliances and gadgets we use at home, such as refrigerators, air conditioners, phones, TVs, and light bulbs. In physics, magnetism is the study of the phenomena by which materials exert an attractive or repulsive force on other materials. Electricity and magnetism are fundamentally linked. Electromagnetism is used in many technologies, ranging from motors to CAT scan machines. Quantum and nuclear forces. Two of the basic forces of the universe, the strong and the weak forces, are observed only on the atomic or nuclear scale. Though we can't directly see these forces in everyday life, we do experience their effects daily. For example, when we see the sun in the sky, we are seeing nuclear fusion at work. It is the sun's source of energy. Quantum mechanics is the branch of physics that studies the motions and interactions of submicroscopic bodies, such as atoms, atomic nuclei, and elementary particles. Quantum laws provide formulas and designs for electronic devices, nuclear reactors, and superconductive magnets. Many modern inventions are based on quantum laws, including lasers, transistors, microchips, electron microscopes, and magnetic resonance imaging, MRI. Physics not only contributes to our technological infrastructure, but also forms the basis for future technological advances. It provides us the fundamental knowledge to understand and develop new techniques and technologies. Many professionals apply their knowledge of physics in their work. Mechanical, civil, aeronautical, electrical, chemical, and hydrological engineers all rely on the principles of physics. Medicine has also benefited. Think of the X-ray, MRI, CAT scan, colored Doppler tests, ECGs, resonance imaging, and radiation therapy, all advanced techniques that detect, manage, or cure ailments. Medical equipment, ranging from simple blood pressure monitors to complex heart-lung machines, pacemakers, and dialysis, were invented and improved through our understanding of physics. Physics also enhances our knowledge of other fields, such as agriculture, environmental science, and forensics. Let's take a look at how physics is related to other sciences. How physics links to biology and chemistry. Physics is a fundamental or basic science. It has a close connection with both biology and chemistry. Biology, as we know, is the study of life. Medical students study how different organs function. However, they also need to know the laws of physics to understand body functions. For example, regulation and circulation of body fluids follows the laws of physics governing temperature, pressure, volume, and density. Nerves carry electrical impulses that hold messages to and from the nervous system. These impulses follow the laws of physics, as do our body's organ systems. Physics and chemistry are linked too. The discovery of elements and their atomic structure is closely related to physics. In fact, the theory of atoms was largely developed through experiments in atomic and nuclear physics. Quantum mechanics ultimately explains how elements combine to form compounds. Physics also explains gas laws, chemical energy changes, the shape of a molecule, and the kinds of bonds formed between atoms. How physics links to Earth and space science. The tools and laws of physics are essential ingredients for an understanding of space and cosmology. Optical and radio telescopes, instruments that employ the properties of waves and optics, help scientists unravel the mysteries of the universe. The invention of space stations, satellites, rockets, and space shuttles took humans into space, further expanding our understanding of our world. These inventions were based on various laws of physics. The movement of heavenly bodies can be explained in terms of the physical phenomena of gravity, relativity, mechanics, thermodynamics, electromagnetic forces, and quantum mechanics. Closer to home, Earth science also borrows heavily from the laws of physics. The structure and dynamics of Earth's interiors involve heat, pressure, and mechanics. Weather forecasters who work with atmosphere and weather systems must understand volume, pressure, velocity, density, heat, and electromagnetism. As you can see, physics not only helps us understand many other scientific disciplines, it also contributes to new technologies that improve the world we live in. Match each activity to its respective scientific discipline. Drag the items on the left to the correct location on the right. Galileo Galilei. Galileo is considered to be the first modern scientist, as well as the first modern physicist. His work became the foundation for Newton's work in defining the field of mechanics. Galileo was fascinated with telescopes and the heavenly bodies. His most important contribution, however, came from the application of mathematics to the study of motion. Most of his research focused on finding out how things move. As a result, Galileo was the first scientist to reveal the basic structure and working rules of the universe. When Galileo was a professor at Pisa, he is said to have dropped 2 cannonballs of different weights from the Leaning Tower to assess the speed at which both the balls descended. Galileo carried out numerous experiments on the relationship between distance and time. One of his experiments involved the swinging chandelier he saw at a cathedral in Pisa. Galileo timed the swings with his pulse rate, which was the only timing device he had at that time. He then observed that the time taken to swing through one complete cycle depended on the length of the chain holding the chandelier. This observation is the basis of his pendulum theory, which paved the way for the first accurate clocks. Because of Galileo's unique way of observing, experimenting, and deriving theories, he is considered the father of modern science. Galileo's experiments discussed here are only a few of those he performed during his lifetime.
你们到 activity 的时候呢，它会有一些细节的，然后你可以看到这个小箭头，蓝色箭头就表示这里有个 link，我一般是肯定会打开的。所以呢，我打开之后，它就进入到一些什么 article 啊什么之类的，这是一个叫 famousscientist.org，不错哦，可以给大家分享一下啊，待会儿分享。有1000 top 100 scientist， 然后你可以稍微读一下。这什么东西啊 ？Recent Scientist of the Week， OK。然后呢 ，Lifetime in Contest， 这是他，然后他前面的人，他后面的人，所以 Isaac Newton 在他后面，干净呢大概在这个时期，15，然后 Isaac 他们两个的 O level 几乎是0。他喜欢 Math, Music, Physics, Art。I did not know he liked art too。不错，可以读一读。OK。
Which of Galileo's theories drew fire from the Catholic Church and led to his house arrest? According to Galileo's pendulum theory, which factor determines the time taken to swing through one complete cycle? Summary. Physics is the scientific study of matter and energy and how they interact with each other. It's a basic science that deals with motion, forces, energy, heat, waves, electricity, and magnetism, and the structure of matter, down to the subatomic level. It forms the base for other branches of science, including chemistry and biology. Physics permeates our daily lives in many ways. Our reliance on technology underscores the importance of physics every day. All of the technologies and gadgets that we use can be traced back to the laws of physics. Some of the many branches of physics are noted here. Mechanics, the study of forces and motions of bodies. Thermodynamics, the physics of heat. Acoustics, the study of sound and sound waves. Optics, the study of light. Electromagnetism, the study of electrical and magnetic fields. Electronics, the study of the flow of electrons, generally in a circuit. Quantum mechanics, the study of how matter and energy behave at the molecular, atomic, or nuclear levels. Many scientists have discovered the phenomena that describe the laws of physics. One of the earliest and best known among them is Galileo Galilei. He was one of the few scientists of his time to challenge Aristotle's existing theory about the motion of Earth and Sun. After conducting several experiments, Galileo concluded that Earth moved around the Sun and not the other way around. Galileo was well known for his method of inquiry to understand events. His most significant contribution to physics is related to the motion of bodies. He determined that two objects dropped from a height fall at the same speed, regardless of their weights. He also defined the law of pendulums, which was employed to devise the first accurate clocks. Introduction. Everything in the universe is in motion with respect to something else. Earth revolves around the Sun, and the Sun orbits the center of our galaxy, the Milky Way. The study of motion is called kinematics, and it's central to understanding physics. In physics, motion is defined as a change in the position of a body with respect to a reference point. For example, imagine you're sitting in a moving train. With the train as your reference point, a bottle of water held steadily in your hand is static. It's not in motion. But now imagine a man standing outside on a road looking at the train. With the solid ground as his reference point, he sees you, the bottle, and the train all traveling at the same speed and in the same direction. Now imagine cars in different lanes moving along a freeway. Think about the motion of three cars, one in the fast-moving carpool lane, another in the middle lane, and the third in the slow lane used to enter or exit the freeway. What affects each car's motion? Where will each be after 2 seconds? What factors determine how far each car will travel over time? What type of motion are these cars displaying? Kinematics answers these kinds of questions. This lesson will cover 17th century scientist Galileo Galilei's experiments to measure and predict motion. You'll study how to describe motion that includes direction, the factors that affect motion, such as friction, and the different types of motion. The lesson will also introduce the concept of inertia and how it relates to motion. Properties of motion. What comes to your mind when you think of motion? A tennis ball flying across the court? Someone doing stunts on a skateboard? Or maybe an amusement park with rides going up, down, forward, and around in circles and spirals? A simple definition of motion is any movement or change in an object's position. For centuries, philosophers and scientists have tried to understand motion and its properties. The Greek philosopher Aristotle presented the earliest written theories about motion. These theories were widely accepted from 500 BC to the early 1600s. Then the Italian scientist Galileo Galilei recorded careful observations and experimented with motion. His observations caused him to challenge what Aristotle had proven 2,000 years earlier. Galileo's work marks the beginning of modern science. Before getting into what Aristotle thought about motion and how Galileo overturned his theories, we need to explain a few concepts to better understand motion. These concepts include distance, displacement, speed, velocity, and acceleration. Distance and displacement. In physics, distance is the length measured between 2 points. Total distance is the distance measured along a path, no matter how complex that path might be. Distance is a scalar quantity, a quantity that specifies only a magnitude, a numerical value, but does not specify direction. Displacement is defined as the shortest path from an initial position to a later position. Displacement is a vector quantity, a quantity that specifies both magnitude and direction. To understand the difference between distance and displacement, think about this example. In your school, you walk 20 meters north from your first hour class to the physics lab. Once your physics lab is over, you walk another 30 meters east to the cafeteria to have lunch. The total distance you cover is 50 meters. However, that isn't the shortest path to the cafeteria from your classroom. The shortest route would be about 36 meters and about 34 degrees north of due east. This measurement is your displacement. It specifies both magnitude and direction. Speed. Speed is an object's rate of change of distance over time. The formula for speed is s equals d over t. Imagine a car moving rapidly from a stopped position. Its initial speed is 0, but its average speed during the first 3.8 seconds is 4.5 meters per second. Using a little algebra, we can modify the speed equation above to solve for distance. st equals d. So, 4.5 meters per second times 3.8 seconds equals 17.1 meters. Average speed, however, doesn't really tell us the whole story of this little car. It started out at 0, so to reach an average speed of 4.5 meters per second, it must have gone well over that speed somewhere along the way. In fact, after 3 seconds, this car traveled at over 7 meters per second. A car's speedometer shows instantaneous speed, the speed at a particular instant in time. That's typically what we're interested in when driving. On the other hand, if we want to know how fast we traveled overall during a long road trip, we'd calculate the average speed, the total distance covered divided by the total time. Note that speed, like distance, is a scalar quantity. It specifies magnitude, but not direction. Velocity. Velocity is different from speed because it specifies direction in addition to speed. Let's use a moving bus to illustrate velocity. During the morning, the bus moves to the east at 20 meters per second from its starting point. In the evening, from the same starting point, the bus moves 20 meters per second to the west. For clarity, we can rewrite this information. Velocity in morning equals 20 meters per second toward the east. Velocity in evening equals 20 meters per second toward the west. This example tells us that velocity is the speed of an object, in this case, the bus, and the direction in which the object changes its position. So to calculate velocity, we consider displacement and not only distance. Because displacement is the change in the position of an object, velocity is defined as the displacement of an object over time. In our bus example, if east is the positive direction, the velocity in the morning is positive 20 meters per second, and the velocity in the evening is negative 20 meters per second. Velocity. Acceleration. When an object's velocity changes, its speed, direction, or both speed and direction change. Change in velocity over a period of time is acceleration. Like velocity, acceleration is a vector quantity. To calculate acceleration, divide the change in velocity by the change in time. For example, say a car starts at rest, 0 meters per second, and accelerates at a nearly constant rate for 3.0 seconds. At 3 seconds, it has a velocity of positive 7.2 meters per second to the east. What is its average acceleration? Average acceleration equals 7.2 meters per second over 3.0 seconds, equals positive 2.4 meters per second squared. The change in velocity here is toward the east, the positive direction. The acceleration then is a positive velocity change divided by a positive time change. Acceleration here must be positive, accelerating toward the east. Now that you've studied the basic measures of motion, let's see what Aristotle and Galileo had to say about an object's motion. According to Aristotle, the speed at which an object falls is directly proportional to the object's mass. For example, a 1 kilogram rock falls to the ground 1,000,000 times faster than a 100 milligram feather. He also claimed that the object's speed was inversely proportional to the density of the medium it was falling through. For example, an object falling through air falls faster than an object falling through water. Aristotle put forward these two theories, believing that an object is always subject to the influence of some medium, such as air or water. According to Aristotle, a vacuum, a void without matter, couldn't exist. Aristotle's theories reflected everyday experience and common sense logic. They were believed, studied, and taught, until Galileo's motion experiments proved differently. Galileo's education included studying Aristotle's theories of motion, but his own experiments and observations conflicted with those accepted theories. Galileo described dropping objects of different weights from the top of the Leaning Tower of Pisa in Italy. His observations led him to realize that objects of different weights dropped simultaneously landed on the ground with just a slight difference in time. Based on this information, Galileo refuted Aristotle's theory that a stone double the weight of another stone would hit the ground sooner. But when a feather and a rock are dropped from the same height at the same time, doesn't the rock hit the ground first? Yes, but that's due to air resistance, not the weight of the object. In a vacuum, the feather and the rock would hit the ground at the same time. Whether in the lab or on the moon, you can observe what happens when a rock and feather are dropped in a vacuum. Types of motion. There are 3 types of motion: translation, rotation, and vibration. Let's look at each one with some examples. Translation. Translation is motion from one point to another. There are 2 types of translation: linear motion, where the object moves in a straight line, and curvilinear motion, where the object moves along any path that is not linear. Think about the cars on the freeway again. If the road is straight, the cars display linear motion. If the road is curved, as the cars go along each curve, they display curvilinear motion. Rotation. When an object spins around an axis without altering its position in space, it is rotating. Simple examples of rotational motion include a spinning top, a ballerina twirling in place, and Earth rotating around its axis. Vibration. Take a rubber band and stretch it across 2 fingers. Now pluck it. It vibrates back and forth quickly. Your cell phone probably has a vibrate setting, which makes the phone vibrate when someone calls. Stringed instruments such as the guitar, violin, and cello display vibrational motion to create music. Sometimes an object may display more than one kind of motion. A car's tires display linear motion as they go forward, but also rotational motion as they spin around the axle. You can see all 3 types of motion at an amusement park. Let's look at some amusement park rides and see what type of motion occurs in each. Types of motion. Click each ride to see which type of motion it demonstrates. Match the object to the types of motion. Click each ride to see which type of motion it demonstrates.
我没有时间再继续下去了，就这样了啊，大家应该有个sense了。好，谢谢，拜拜。